Usually, when I start to fiddle around with a new synth, one of the first controls I want to tweak after playing a note is the pitch bend control. So here we are, we have a basic saw voice, a way to play notes, and now we're going to bend them. If you'd like, you can flash the pitch bend project to your BP synth to see it work. Please refer to previous videos for instructions on how to flash the code and hook up a keyboard to your BP synth. Once you have the code flashed to the BP synth, you can give it a try. If you happen to have the GUI connected up, there's a feature you can use called MIDI Monitor. Let's open that up and set it up now. On the GUI, click on Tools. Then click on MIDI Monitor, and then you'll see this window open up. Now if you press a few notes, you can see the notes displayed on the output window and the input window. Over here you can click on View, and for now I'm going to disable Monitor Input, so now we should only see the output notes. And I can even split the window down so we don't see the input window. Now if I move the pitch bend wheel, we can see the MIDI messages for that. And there's a lot of information we have here. When we click on View, we have Show Name, Show Channel, Show Number, Show Value, Show Raw Data, all enabled. This is the name of the message, pitch wheel. This is the channel. And this is the value, and here's the raw data in hexadecimal form. So what we're seeing here is live data streaming from the keyboard to the VP synth. Now that we can monitor the MIDI messages coming from the keyboard, I'm going to show you a difference between pitch bend messages sent between two different keyboards. Let's start with the Axiom keyboard. When I pitch bend using this Axiom keyboard, you will see the message going by. It shows Now let's observe the MIDI pitch bend messages from the Akai keyboard. See the difference? The Axiom was only changing the second data value, but the Akai was sending both first and second data values. Soon we will see what the data values are used for, how they are used in the code, and why there are only one or two data values used. Pitch bend values are usually a 14-bit value. Its range is 0 through 16,383. The pitch bend command byte message is E followed by the channel number. In this case, E0 is pitch bend channel 1. An example pitch bend message would look like this: hex E0, hex 5C, hex 80. We're going to see how we get a 14-bit value from 8-bit numbers. Remember, MIDI only talks in 8-bit words. Let's go to Atom and open it up, and let's go over to BP, Pitch Bend, Core, Source, Main.c. Let's scroll down to a function called Do Pitch Bend. Here is the Do Pitch Bend function. Now let's take a look at what's going on in here. This first operation, unsigned integer 16t, pbend MSB equals MIDI velocity. What we've done is we're creating a variable called PitchBend MSB, and MSB is short for most significant byte. pbend MSB is going to be a 16-bit value. So it's going to use 16 bits versus MIDI velocity, which is cast as an 8-bit number. So the data in MIDI velocity will be saved into PitchBend most significant byte, but it will be saved as a 16-bit number instead of a 8-bit number. The same thing happens with the next operation. PBend LSB, short for least significant byte, equals MIDI note. Following that, we have PBend MSB equals PBend MSB bit shift 7 bits to the left. And we'll get back to this in a moment. The next operation, we are casting another local variable called PBend val. But we're going to be ORing the data from both PBend most significant byte and PBend least significant byte. Again, we'll go over this here in just a moment. Next we have float map pitch equals PitchBend value minus 8192. What we're doing is we're remapping the PitchBend value and calling it map pitch. Next we have float semi pitch equals map pitch divided by 8192. Next we have adjust semi pitch equals semi pitch times bend range, and bend range is a multiplier so that you can go up or down so many semitones. So if bend range is 1, the maximum it will pitch bend up or down is 1 semitone. If bend range is 2, which is the default right now, it will have a maximum pitch bend range of 2 semitones up or down. The next operation is float prebend factor equals adjust semi pitch divided by 12. This is similar to what we did in our MIDI note to frequency conversion, where we have 1/12 of an octave for each semitone we go up. And then finally we have bend factor equals 2 to the power of prebend factor. And this will become our final value that we will multiply against the frequency. Notice that PBend MSB is using the value from the second data byte, MIDI velocity, and PBend LSB is using the value from the first data byte, MIDI note. You would think the first data byte would be the most significant byte, and the second data byte would equal the least significant byte. But in this roll, they are reversed. That is why when we saw the axiom only send the second data byte while bending, it was able to meet the range of 0 to 16,383. More on this in a bit. The action we need to understand first is how we get a 14-bit value out of two 8-bit numbers. We have to change or cast the two 8-bit values to 16-bit. Thus, a 8-bit value of 9 would look like this: 00001001. Cast it to a 16-bit value and it looks like this. So let's say PBend MSB, which was the second data value, is this value now. We take PBend MSB and bit shift it to the left by 7 bits, like this. Now the data value is this. Let's give PBend LSB, which is the first data byte value, a value of 32, which casted to a 16-bit value would be 00000000100000. So now we have completed this part of the code. Next, we need to OR them together, which is this part of the code. So we're going to take the value from PBend MSB, which is our bit shifted value, and we're going to OR it with the value from PBend LSB, which was not bit shifted. When we OR these two values together, we end up with 00000101000000, which is 1184 in decimal value. Remember at the start of the lesson I showed how two keyboards send pitch bend messages in different ways? One was sending only most significant byte values, while the other was sending both most significant byte and least significant byte values. Now you can see that you can still shift the most significant byte value 7 bits to the left in a 16-bit cast variable and still get the values that range from 0 to 16,383. But the first value past 0 will be 128. After that, 256. Then 384. We're incrementing up each time by 128 since we don't have any bits to set in the first 7 bits of our 14-bit variable. 128 values with each step equals 128 will total out to be 16,384, or 128 times 128. But we max out at 16,383 because we include a 0 in there as one of the 16,384 values. Recall that the bender's range is 0 through 16,383. The bender's center point is where we don't want to alter the original frequency. We only want it to change if we move it past or before the center point. Half of 16,384 values is 8,192, our bender's center value. So when we do float mat pitch equals p-bend val minus 8192, what we are doing is remapping the value of p-bend val so that the center value becomes 0 instead of 8192. If p-bend val is less than 8192, we'll end up with a negative value. If it's greater than 8192, we will end up with a positive value. In similar fashion to what we did with converting a MIDI note number to a frequency, we will be using a base of 2 exponent in our code. So negative values will become fractional values less than 1, and positive values will become fractional values greater than 1. And if we have a value of 0, we end up with a 1 after applying the 2 base exponent, which won't change the frequency at all. Let's give the function a try with a value of 9,000. p-bend val equals 9,000. 9,000 minus 8192 equals 808, a positive value, which means we're pitch bending up. 808 divided by 8192 equals 0.0986328.125. 0.0986328.125 times 2, which is our pitch bend range, equals 0.197265625, and then 0.197265625 divided by 12 equals 0.01643880283. This is where we're dividing by 12 for our semitone. Then 2 to the power of 0.01643880283 equals 1.01145967408. This is going to be our value we used to multiply against our base frequency. So now we multiply our frequency to our bend factor value. In this case, a frequency of 110 times 1.01145967408 equals 111.260.564.140908. So we bent our note up from 110 Hz to 111.261 Hz, not even half a semitone. With our bend range equals 2, meaning it will range up or down by 2 semitones, we can predict what it takes to reach the next semitone up. is going to need to be 50% up from center. 50% of 8192 is 4096. Let's run with that. If we add 8192 to 4096, we get 12,288. So let's take 12,288 minus 8192 equals 4,096. This is our remapped value. Then we take 4,096 and divide it by 8192, and it equals 0.5. 0.5 times 2, which is our bend range, equals 1. 1 divided by 12 equals 0.083333333333. Then 2 to the power of 0.083333333333 equals 1.059463094,359. Now let's multiply against our base frequency of 110. 110 times 1.059463094,359 equals 116.540940379496. When we check our note to frequency table, we can see the next semitone past 110 Hz is 116.5409403795. Amazing! We hit it dead on, didn't we? What if we bend down a semitone? Let's see what happens. 4,096 minus 8192 equals negative 4,096. Negative 4,096 divided by 8192 equals negative 0.5. Negative 0.5 times 2 equals negative 1. A negative 1 divided by 12 equals negative 0.08333333333. 2 to the power of negative 0.08333333333 equals 0.943874312682. And when we multiply it against our base frequency of 110, we get 103.82617439501. And our note to frequency table says the semitone below 110 Hz is 103.826174395. Again, we're spot on. Now let's modify the code in wavegen.c so we can apply the PitchBender to our note frequency. So in Atom, let's just go ahead and take a look at wavegen.c. And you'll see right here, bend factor is multiplied against our original MIDI note to frequency conversion. It's fairly simple when you get to this point. I probably explained this code more than is required to use it, but the mystery of how we get our values to increase or decrease the frequency accurately when we move the PitchBender should now be more clear. We could create a control later to change bend range to be either very mild to extremely wild, but I tend to like to leave it at 2 because that's how most synthesizers are set. Next, we're going to start taking a look at control changes, starting with the volume control.